Section 1110 continued, Taylor and Maclaurin series, but this time let's explore the binomial series. So let's take the binomial 1 plus x to the k. And notice here we have in previous courses, pre-calculus courses, looked at this expansion when k has been an integer, and we've used Pascal's triangle, and we've expanded this binomial out, and looked even at maybe the patterns in the coefficients as we go. But here we're not even going to specify that it has to be an integer. Here we're going to, that's kind of a sloppy R, but here we're going to talk about k is actually going to be any real number. So we can even be looking at like a square root here, or a negative exponent. So this is where k can be any real number. And so let's get started. And first let's figure out what would this power series expansion be when we're centered at 0, when we're looking at the Maclaurin series. So remember again, when we hear that phrase Maclaurin, we're looking at a Maclaurin series. That's a Taylor series expansion. We are just centered at x equals 0. So that's kind of the thought as soon as we read the word Maclaurin. So we're going to take this, we're going to be centered at 0. We will make the assumption that it does in fact have a power series representation. Again, that's that takes a little bit of time to show. So we will make that assumption, and if it does, then this is what it would look like since it's a Maclaurin series. F of x, 1 plus x to the k, would be equal to the power series c sub n times x to the n. And those coefficients, c sub n, would be equal to the nth derivative evaluated at 0 and divided by n factorial. So that's the key. That's what we have to figure out by looking at some derivatives and figure out what is that going to look like. What is that nth derivative? What's the pattern that occurs in the nth derivative when we evaluate it at 0 and then divide by n factorial? So to do that, let's go ahead and make a little table. I like to organize my work in a table. I think it makes it a little easier to see what the patterns are going to be. So we'll look at n's. Let's go 1, 0, 1, 2, 3. We don't need to go that far. 4. That should be enough. If we need to, we could do some more and see if we can come up with what the nth derivative is, an expression for the nth derivative. So remember that the 0th derivative is the function itself. So the 0th derivative is just 1 plus x to the k. Now the first derivative, we're going to apply the power rule, and that is going to be k times 1 plus x to the k minus 1. Now, technically, we would apply the chain rule and we would be multiplying by 1 right here. For the further derivatives, the future derivatives, as we keep going down this pattern, I'm not actually going to write that. But that's not to say that we shouldn't think about that, because if there had been a 2x in there, then we would have to, of course, account for that. Okay, so we have that first derivative. So then the second derivative, we continue, and we're going to get k times, again, we bring down the power, k minus 1, and then we have 1 plus x to the k minus 2. And for the third derivative, we're going to have k times k minus 1 times k minus 2 times 1 plus x to the k minus 3. And that might actually be enough to see what's happening with this pattern. Notice that we're getting a product of factors here as we continue to bring down the powers. And so we have a product of 3 factors here. By the fourth derivative, we're going to have a product of 4 factors, k times k minus 1 times k minus 2 times k minus 3 times 1 plus x to the k minus 4, and we can hopefully see what the pattern is going to look like here. Every time we do this, we're going to bring down a power. So by the time we get to the nth derivative, I don't know, think like the 100th derivative, we're going to have k times k minus 1 times k minus 2 all the way out to k minus n plus 1. So we'll be all the way out to k minus n. So, think about the fourth derivative. We would be at k minus 4 plus 1, because we're really only subtracting minus 3 by the last one. So k minus n plus 1 times 1 plus x, because it's to the k minus n, because we've taken n derivatives here and applied the power rule n times. Okay. All right, so we have a pattern for what the nth derivative is going to look like, and so now we can put that into the coefficients and see what would then the coefficients be. So remember, the coefficients we're actually going to be plugging in, since we're centered at 0, we're actually plugging 0 in to that derivative, to those derivatives, and then dividing by n factorial. So for the first one, when I plug in 0, notice I'm just going to get 1 to the k over 0 factorial, which is 1. And then for the second derivative, for the first derivative, for the second row in my columns here, I'm taking the first derivative, so if I plug in 0 here, I'm going to end up with k times 1 over 1 factorial, which would just be k over 1, and then on to the second derivative, k times k minus 1 over 2 factorial, and I'm going to stop expanding the factorials here. We'll just leave them as factorials. By the third derivative, k times k minus 1 times k minus 2 divided by 3 factorial, and the fourth derivative, k times k minus 1 times k minus 2 times k minus 3 divided by 4 factorial, and for the nth coefficient, we're going to have this entire thing, k times k minus 1 times k minus 2 out to k minus n plus 1, and then we just have 1 to a power, so that's just 1 times 1, all over n factorial. And we have found what the coefficients look like. So for this series, we have found what our c sub n's look like. So our c sub n's are going to be equal to this expression that we just found. So our c sub n's are going to be k times k minus 1 times k minus 2 out to k minus n plus 1 divided by n factorial. Okay, now just so you know, this is actually an expression that comes up in probability and combinatorics, and so it gets its own little special notation. We can also reference it to some factorials. So just some other notations. We can write this as k choose n. That's actually how we say that. We say k choose n. That comes from the connection to probability. Combinatorics. So that comes from its connection to probability and combinatorics, but it is nice shorthand for this exact expression. That is also equal to, we could also write that as a ratio of a couple factorials, k factorial over n factorial times k minus n factorial. If we think about how we ended with this expression right here on the top, you could think of that if that continued and went all the way down to 3, 2, 1, that would be the factorial k factorial, but it doesn't continue. It stops at k minus n plus 1, so that means we've taken off the k minus n factorial or divided by the k minus n factorial. So these are just other ways to express it. These are just other ways to express c sub n if we were to want to express them that way. Okay, I'll probably use these two. I don't know that I'll use the factorial one, but we may, so I'll just write those in there. All right, so we have everything we need now to actually write the Maclaurin series for this binomial expansion. So let's go ahead and do it. So we can say this. We can say if I can squeeze this in here without getting too sloppy. Thus, therefore, f of x, which is equal to 1 plus x to the k, can be expressed as the power series n equals 0 to infinity. I will, on my first line, write it this way as k choose n, x to the n, but I will also write it in its expanded form, a little more useful to work with. So that is equal to those coefficients that we found, k times k minus 1 times k minus 2 out to the factor k minus n plus 1 divided by n factorial times x to the n. And if we were to actually write that out, and I do want to write out a couple of terms here. If I were to start just writing out a couple terms, what that's going to look like is 1 plus k times x plus, and we actually had those, I could get those there. There we go. So there's the first couple coefficients. So the first coefficient's 1, the second coefficient is k over 1, and then we can keep going. So, and I'm going to write out a couple of those coefficients there, or we could just use the formula we derived here. And so then that's going to be k times k minus 1 over 2 factorial times x squared plus k times k minus 1 times k minus 2 over 3 factorial times x cubed. I think it's nice to always see what a couple of those terms look like. There's so many symbols and mathematical symbols and operations in the power series, especially this particular one, when we write it in the power series form. And so sometimes it's nice just to see, like, that is that infinite polynomial with those coefficients expanding out. Okay, this is what we call our binomial series, and we're going to add this to our useful set of series here in just a second. So this is what we call the binomial series. And I just want to mention here for a second that if, well, let's make a note on this one. If k is a positive integer, this becomes a finite sum. And we could actually just expand using the series here, or Pascal's triangle, right? We've looked at these in their finite sums before, so here's just a quick little example. Like if we had, let's say, I don't know, what do we want to do? 1 plus x to the 4th. So recall here. Quick little recall on this one. 1 plus x to the 4th, if you think about Pascal's triangle here, and I won't spend a lot of time explaining Pascal's triangle, I'll just generate it. That is a topic for another day. So continuing just little Pascal's triangle, this is the line we need if we're going to go out to the 4th. These are the coefficients we would have, and this would be 1 plus 4x plus 6x squared plus 4x cubed plus 1. X to the 4th, if we were to expand this out. But it turns out that that is exactly the same as doing 4 choose n from n equals 0 to infinity. I'm sorry, n equals 0 to 4, actually. It becomes a finite sum, x to the nth. And so that turns out we could show that that's the same as taking 4 choose 0 times x to the 0, 4 choose 1 times x to the 1st, 4 choose 2 times x squared, 4 choose 3 times x cubed, and 4 choose 4 times x to the 4th. And then the rest of the terms, actually, we could have put infinity there. The rest of the terms would zero out in this particular power series expansion. But this ends up giving us those exact same coefficients. So we could work that out, but I'm going to leave it at this. So just wanted to make that quick little note before we go back and find the radius of convergence. But that is kind of a little interesting fact. We're looking at this and we're going to be more interested in the infinite sums when this is not necessarily, when this power here is not necessarily a finite, I'm sorry, it will be finite when it's not a positive integer. So we'll be looking at expanding these in that way. But just as a note, we can actually use this as we have in the past with Pascal's triangle. It works out the same way. Okay, so that was kind of a little side tangent, but let's go ahead and hop back into what is, when can we do this? When can I use this equality? What is the radius of convergence? So when can I make this claim that this binomial 1 plus x to the k is equal to this power series? So when can I do that? So let's come back here. I have that little side note here. And so let's come back actually, and I'm going to move that off to the side. And let's find the radius of convergence. So if this is our binomial series, what is its radius of convergence? So let's find the radius. So let's get in here and actually do a ratio test. So let's take L, I'm going to zoom in a little bit here. Equal to the limit as n approaches infinity of the ratio of the powers of the n plus 1 term. So we'll have k choose n plus 1 to the x over n plus 1, and k choose n over x to the n. And let's see what we get there. So when we do that, when we expand that out, obviously the x is reduced and we have just the absolute value of x. I'm going to put that on the outside. So the absolute value of x times the limit as n approaches infinity. And then the k choose, so let's do this part first, the k choose n plus 1. That is going to give me k times k minus 1 times k minus 2 out to k minus n plus 1 plus 1, which, by the way, will become just k minus n all over n factorial times, I'm sorry, n plus 1 factorial. I was looking ahead. And then on the other side, we have n factorial and then k times k minus 1, k minus 2 out to k minus n plus 1 in the ratio. Okay, quick note, the factor right before this factor is going to be k minus n plus 1. So just keep that in mind, because when I do my reduction here, everything is going to reduce in this expansion except for this piece, which is those two are equivalent. And in the expansion of the two factorials, there's going to be one extra factor in the n plus 1 factorial from the bottom. And so this ends up becoming the absolute value of x times the limit as, once I get through all that reduction, I end up with just k minus n over n plus 1. Okay? As I go through that, as I expand out those coefficients, and then I do the reduction. That's all I end up with. And so that is in absolute value. I can't drop the absolute value because we don't know if k is we don't know if k is positive, negative, fractional, whatever. We don't know in this proof. We have let k be any real number. So we'll leave it as is in the absolute value. This is going to become the absolute value of x, and then the limit as n goes to infinity. K is a constant, and so what would be helpful right here is if I multiplied top and bottom by 1 over n, and then this is going to become the limit of the absolute value of k over n minus 1 divided by 1 plus 1 over n. Now, the denominator is positive, so I did leave the absolute values just in the numerator, but we could have left them on the denominator as well. Okay. And so as we go, it turns out it doesn't matter what k is a real number. And so as n approaches infinity and grows without bound, this will eventually approach 0. This will also approach 0. And we end up with the absolute value of x times 1. And so by the ratio test, whatever this limit is right here, this L that we've defined, and the limit has come out as just the absolute value of x, that will converge when that is less than 1. So we will have convergence by the ratio test when x is an absolute value less than 1. And what that tells me is that the radius is equal to, I almost wrote infinity, but 1 is not infinity. 1 is definitely not infinity. Okay, so there we go. So the radius is actually equal to 1. So the radius for this binomial series expansion is equal to 1. So we could summarize this all up. I've got it all here on the screen now. So we can summarize this and we can say that our f of x equals 1 plus, so we've actually verified now, we figured out what that radius is. So this function f of x equaling 1 plus x to the k for any real number k, doesn't matter what k is, that is actually equal to the power series from n equals 0 to infinity of, the coefficients are going to be k choose n, x to the n, and that k choose n by definition is actually n, so this is n equals 0 to infinity of k times k minus 1 times k minus 2 out to k minus n plus 1 over n factorial times x to the n for the absolute value of x less than 1, or another way of saying that, with a radius of convergence equal to 1. Get that up on the screen. And that is our binomial series. And in its expanded form, a couple terms in its expanded form right up there as well. So if we wanted to expand it out a couple terms, we did that earlier. Okay, we want to add that in to what we call our useful series. And so we have a little list of useful series that we have been developing through this entire section, and actually the previous section as well. And so if we look at that, I added it in already and just summarize them all right here. So these useful Maclaurin series, that meaning that we're centered at 0 for all of these. The 1 over 1 minus x came from a previous section, but we have derived either through videos, examples, or possibly had you derive a couple of these on your own through worksheets or on a quiz. But these are our list so far of all of our useful Maclaurin series that we can now utilize. And I have just added down here at the bottom the binomial that we just derived. So here is the binomial series. And we definitely like using these series whenever we want to do work with these type of functions or variations of these functions. And so I'm going to do an example of that to close out this video. I'm going to use what we just derived from the binomial series to write an actual power series of a function that's slightly manipulated, not just 1 plus x to the k, but something maybe that we have to do a little more work on. So let's take a look at that. So let's go into, now that we have it, now that we have our binomial series, let's go and take a look at an example. So let's do this. Find the Maclaurin series and the radius of convergence for the function f of x equals 1 over 1 plus x to the 4th. So we can see right here that this could be written as 1 plus x to the negative 4th, and that can be, you know, the thought bubble here is let's use our binomial series. So we're going to think, okay, we're going to use our binomial series that says 1 plus x to the k, series n of times x to the n from n equals 0 to infinity. Okay, so we think, okay, we know we just derived that binomial series, so now let's utilize it to write another function. So this time we have the 1 plus x, so there's no manipulation that needs to be done here. The power, the k value, is negative 4, so we're going to go ahead and get in here and say, okay, that means that 1 plus x to the negative 4th is going to be equal to the power series from n equals 0 to infinity to the nth. Now, I'm sorry, we should say one more thing. Right, as soon as we've done this little equality, we should always mention that this is true when the radius of x is less than 1. Okay, so we should definitely make that statement. Anytime we take a function and set it equal to a power series, we need to classify or clarify where that is true, on what interval that is true, or on what radius that is true around 0 here. Okay, so now let's think about what does this guy look like. So let's take maybe that off to the side here and think about before I go back to that power series expansion, let's just think about what does that look like. So remember that that is equivalent to saying, that is the same as saying -4, -5, -6, out to -4 minus n all the n factorial. So that is simply the expansion for that coefficient. So we've simplified that coefficient, or we've expanded that coefficient. Now I actually do want to simplify it. So what I would do first here is say, okay, well, this is the same as saying -n minus 3 right here. And I'm looking at that and I'm thinking, you know, each of these factors, by the way, has a negative on them. So each factor here has a negative. I'm trying to highlight those, but my highlighter's not working. Each factor there has a negative. We could factor out a negative from this one, that whole factor there is negative. And so at first I think, you know what, the first thing I'm going to do here to simplify is I'm actually going to just, I want to be able to express this coefficient in a more compact and a nicer way if I can. And so the first thing I'm going to do here is just actually factor out a negative factors here. So when I factor a -1, I can take one from every single one of those factors. I will end up with n of them. So I have -1 to the nth power. By doing that, I now have just 4 times 5 times 6 out to, and now this becomes just n. Now we could leave it like that, and sometimes we do. Sometimes we just, I guess you can decide as you're simplifying these and whatever else you might have to do, because here we're just expressing this function as a power series. I'm going to go ahead and have us also write out a couple of terms here, but we could leave it here, but I can see that there is actually further simplification that can be done that would make this really nice and clean, and I'll show you what it is. This is not a factorial, but it is almost a factorial. So when I'm looking at this and I'm thinking, you know, this is not a factorial because it doesn't have the 1, 2, 3 in it, but it's almost a factorial. I have a factorial in the denominator, and had a little glitch in the video right there and my notebook shut down, but I think we're ready to resume this totally awesome binomial expansion. And so I'm going to pick up right where I left off, or hope I'm going to pick up right where I left off here, which is we have this almost factorial, but not quite a factorial. So what do? Well, we can make it a factorial. All we have to do to make this a factorial is, notice here it's missing the 1, 2, 3 part. So why don't I add that in? Multiply by 1, 2, 3. I can absolutely do that as long as I also multiply by 1, 2, 3 in the denominator. And so if I add in that 1, 2, 3 in the denominator and a 1, 2, 3 in the numerator, look at how nicely this simplifies, and also what I'm going to be able to cancel. So notice now in the numerator, I actually just have the factorial n plus 3. And in the denominator, I have 6, because 1 times 2 times 3 is 6, times n factorial. But now these two factorials are going to reduce, and we're going to have just the 3 factors in the numerator left. And so this actually reduces down to -1 to the nth, and then I'm going to have n plus 1, n plus 2, and n plus 3 in the numerator, because the rest of the numerator has canceled with the n factorial, and all that's left in the denominator is 6. And so that has reduced down my -4 choose n down to a really nice compact -1 to the nth power times n plus 1, n plus 2, n plus 3 over 6. And so we've gotten that reduced down really nicely, and we can actually come back to what we had up here, and we could write this now. I lost it. So we can now rewrite that function, 1 plus x to the -4th, as the power series with those coefficients x to the n where the radius of convergence is equal to 1. And we could even take that further and we could expand this out. We could start to expand this out a little bit, and we could think, well, what's that going to look like? Well, when we plug in 0, we're going to have 1 times x to the 0, so just 1. And then we're going to have -4, and you can go through the calculations on these. I did it ahead of time, plus 10 x squared minus 20x to the third, and so on and so forth as we expand out this power series. So that's what this power series looks like in its expanded form if we start to write out a couple of terms. And so we could do this now. We could even say, I mean, we could ask to estimate, right? If we wanted to estimate 1.1 to the negative fourth power. Well, that's just 1 plus 0.1 to the negative fourth, and that means that x is actually equal to 0.1, and we could plug that in and we could make some estimations. So I am running way over on my video here, but I wanted to make sure that I got in one example where I showed you a little bit of that manipulation, and happy to do some more examples probably during the class sessions, since I've run up against the 30-minute mark, which is way over what I try to do on these videos. So I'm going to wrap it up, but keep in mind we have now derived a whole set of useful power series, and those are going to come in handy. So, make a little table, reference the table in the book, whatever you want to do here. I outlined them right here. Here's our little useful Maclaurin series, but we will utilize these to do things like make estimations, do integrations, all these things that we were, unable to do maybe with the actual functions, we can now do with their power series expansions. And so we've derived a bunch of them and finished off with this binomial series. And so now we can utilize them to do other things and make other estimations.